take a look here at this next example. We're asked to consider this integral. The integral of 1 over the square root of x squared plus 9 dx. We're first asked to evaluate this integral using the techniques of section 8.4. So section 8.4 was a trigonometric substitution. We see that we've got a square root of an x squared plus an a squared, where the a is equal to 3. So that lets us know that we're going to do a tangent substitution. And that's going to turn this square root of x squared plus 9, after we go through the appropriate trigonometric identities, into 3 secant of theta. And that also tells us that dx is 3 secant squared theta d theta. So if I look over here into the land of theta, I've got 1 over 3 secant of theta times 3 secant squared of theta d theta. The 3's cancel out, a factor of secant cancels out, and I'm just left with the integral of secant of theta d theta. And the integral of secant of theta d theta, that's one of those brand new integration formulas we talked about at the beginning of the course. That's a natural log of the absolute value of secant of theta plus tangent of theta plus c. So this is what it looks like here in the land of theta. What's it look like in terms of x's? So to do that, we got to go back to our substitution. And we remember that this is good for thetas between minus pi over 2 and pi over 2, which means we're in quadrants 1 and 4. So let's hop over there and take care of business. If x is 3 tangent of theta, that means that the tangent of theta is x over 3. And I can imagine here we're either in quadrant 1 or quadrant 4. If x is positive, we're in quadrant 1. And so the opposite side having length positive x makes sense because we're above here. We got a positive value here. If x is negative, then that makes sense as well. In both cases, we can solve here. We've got the adjacent side is 3. And in both cases, we can go through the Pythagorean theorem to get our hypotenuse, just like we've always done. So in both cases, I can get to the secant of theta, hypotenuse over adjacent, square root of x squared plus 9 over 3. So that means that when I go back to substitute to get my answer in terms of x's, I get the natural log of the absolute value of secant plus tangent and I can do a little bit of algebra here. That's the natural log of the absolute value of x plus the square root, x squared plus 9 over 3 plus c. And if I wanted to do a little more algebra, I can use some properties of absolute values and logs. The absolute value of the numerator over the absolute value of the denominator. And then the natural log of the numerator minus the natural log of the denominator. The natural log of the absolute value, 3, that's just the natural log of 3. That's just going to get glommed into that constant. Whoops. Do I really need absolute values here? Whoops. I don't know what's going on with my pen today. Do I really need those absolute values? Well, let's think about it. The square root of x squared plus 9, that's clearly going to be bigger than the square root of x squared because I'm adding 9 inside the square root. This is always going to be, x squared plus 9 will always be a bigger number than x squared. And the square root of x squared is the absolute value of x, which is always bigger than or equal to x. So no matter what goes on in here, this square root quantity is always going to be bigger than or equal to x, which means this is always going to be, well, it'll always be bigger than x, I should say, strictly bigger than x. So this will always be positive to begin with. So I don't really need those absolute values. All right? And so this is how we can arrive at the answer for this integral using a trigonometric substitution with our trigonometric functions. However, it asks us to solve this integral using the substitution 3 times the hyperbolic sign. So this is a hyperbolic substitution. Now, depending on how much you did with hyperbolics in Calc 1, you may remember this formula. This might be a formula you remember or you were told to memorize. You may have memorized this as an inverse hyperbolic. If so, good for you. All right, we'll see this come out in the wash with what we do with our what they have us do here on this problem. So here's what they say is, look, we have this problematic integral, really because of this square root. We can use circular functions, the trigonometric functions, and their identities to help us turn this two terms into a single term, and then take this perfect square, take the square root. You can do the same thing with hyperbolics. So let's let x be 3 times the hyperbolic sine of t. So that dx then is 3 times the derivative of hyperbolic sine, which you may or may not recall is the hyperbolic cosine. Remember, the hyperbolics and the circular functions, they're sort of cousins. And we'll talk more about why that's true later in the course. Now, let's look at this, what's going on here in this square root. If I take the square root of x squared plus 9, then that's going to be the square root of 9 sinh squared plus 9. And I can factor that 9 out. 9 times sinh squared plus 1. The 9 comes out of the radical as a 3. 3 times the square root of, and sinh squared plus 1, that's one of those Pythagorean-like hyperbolic identities. 1 plus sinh squared is cosh squared. So this actually works out to be cosh squared. That'd be 3 times the absolute value of cosh. And you may or may not remember that the hyperbolic cosine is a sum of exponentials, which means it's always positive. So I don't need the absolute values. All right? So look what happens over here in hyperbolic. After this hyperbolic substitution, it's 1 over the square root of x squared plus 9, but that's just 1 over 3 cosh t. And then the dx is 3 cosh t. So check it out. Everything cancels. I'm left with the integral of 1 dt, which is t plus c. And what's t? Well, x was 3 times the hyperbolic sine of t, which means the hyperbolic sine of t is x over 3. And you may or may not recall the hyperbolic sine of t is invertible. It's a difference of exponentials. It's 1 to 1. So t here would be the inverse hyperbolic sine. And so here we go. The integral of 1 over the square root of x squared plus 9 dx, if we use a hyperbolic substitution, falls out in basically one step if you go through it that way. Right? The point is that you can exploit those hyperbolic identities the same way we exploit the trigonometric identities to the same ends. And so in like a parallel universe, they may stress the hyperbolic substitutions instead of the circular functions. Now, if we fire up a computer algebra system like Wolfram Alpha, and we ask it to integrate, I'll just type that. It's going to pop up with this inverse hyperbolic. And oftentimes you'll see that. You'll often see the inverse hyperbolics coming up where you would normally have logs. Now, what's interesting is if you want to, in the privacy of your own home, the inverse, or the hyperbolic sign rather, is defined as e to the t minus e to the minus t over 2. And if you want to, you can go through the algebra to find an expression of the inverse hyperbolic sign in terms of logs. So how you would do that is you would switch inputs and outputs here. You call this thing y, and then you would switch. T would be e to the y minus e to the minus y over 2. And you would go about solving for y. If you're interested in that, let me know. It's a nice little excursion into quadratic type equations, and quadratic formula gets involved and things like that. But you can actually find an explicit formula for the inverse hyperbolic sign in terms of logarithms, which then you can backtrack to show those two answers are equivalent. Okay. So once again, hyperbolic substitutions, you can use these identities. If you have a sum of squares, you can exploit this version of the identity to take a sum of squares into a single square. If you have a difference of squares, you can exploit this identity to get it in terms of single square if you have the variable minus the constant squared. And if you have the constant minus the variable squared, then you can exploit that identity to get those two terms to one term. Okay? So it's just something I wanted to make you aware of. And that'll do it for that example.